Hi everyone and welcome to the last evening of Pint of Science Belgium. So I'm Monica and today Flona is also joining us. Hi Flona.
Hi, good evening.
And you're part of Pint of Science Belgium. Probably by this time you already know that Pint of Science is learning science with a beer on your hand. Normally this would take place on bars all over the globe, but everyone has been a bit disappointed with Corona, and therefore we have moved it online. So today, to close with a golden brooch, our Pint of Science Belgium Festival, we have Ben Sommers. So he's a researcher at the KU Leuven, postdoctoral researcher now, and also he performed his PhD thesis in the group of experimental otorhinolaryngology, where he researched cochlear implants and other very exciting processes of the hearing that he will tell us all about today. And he's also very interested in science communication, so I'm pretty sure that the talk he's going to give us is amazing. So welcome, Ben.
Hi, good evening.
Thank you for joining us.
Thank you for having me. Yeah.
The floor is yours.
Okay, thank you very much. So good evening, everyone. I'm very honored to be able to give a talk here, and I hope that we can have a chill talk this evening and talk a bit about brainwaves and audiology. So myself, I'm an engineer by education, but I really wanted to do something more applied. So that's why I got into the lab where I'm currently working, because it's very interdisciplinary, where we combine a lot of neuroscience and audiology and medicine with nice also engineering and technology. So the goal of the evening for me is to talk a bit about some research that I did together with colleagues about some innovative techniques about bringing brainwave measurements to audiology to help people hear better. And most of it will be also about things that I investigated during my PhD. So first of all, before we get started about all these fancy audiology and technology things, let's take a step back and just look at what a healthy ear looks like. So this is maybe something you recognize from your biology classes from when you were a teenager. The sound will come into the ear, and the first thing it touches there is the eardrum, and it's literally a drum that moves back and forth when there's a wave coming onto it. Then it puts into motion the hearing bones. These are actually the smallest bones in the human body, and they make sure that the translation or the vibrations of the sound get transmitted to one of the most important organs that we talk about this evening, the cochlea. If you can see here, the cochlea, it also has like a little window at the entrance where the stapes, that little bone, connects to, and that's basically where the pushing motion caused by the vibrations of sound is transmitted into the cochlea. You can think of the cochlea as basically a big tube filled with liquid, and in that liquid there will be some waves, and those waves will set in motion some hearing hair cells, and those then transmit the sound to the auditory nerve. Now, I went over this a bit quickly. So how does it actually work within the cochlea? So within this tube of liquid, you actually have certain membranes, and on this membrane, due to the motion of the liquid, there will also be some waves traveling, and these waves will set into motion these hair cells. So that's probably something you heard about, hair cells. This is also the little cells that die off if you get older. This is causing hearing loss when you get older, or when you're listening to too loud music, then they also die, and they unfortunately do not regenerate. So the motion of these hair cells then gives a little electrical signal to the nerves that are connected to them, and then these nerves, they continue on and they transmit the signal to the brain, where the sound is actually processed by neurons firing and interpretations going on all over the place, which is a very complex process. One interesting thing about the cochlea is that it is frequency sensitive. So this basically means if you look at this like a snail house or the spiral that is curled up, the different hair cells along this spiral, they are sensitive to different frequencies. So at the entrance, or the base, as we say, of the cochlea, we hear mostly high frequencies, and as the wave travels further down the fluid, the high frequencies get filtered out. So that means that at the end, or at the apex, the tip of the cochlea, we hear mostly low frequencies. So this is actually an interesting property that I will come back to in a moment when I talk about how cochlear implants work. So what if you now have problems with hair cells that start dying when you're too old or when you have a certain disease? Yeah, you can, of course, get a hearing aid. And the hearing aid is basically an amplification. So you can still hear sounds, but it's just a lot softer because there's not so many hair cells that are transmitting the sound anymore. So yeah, hearing aid is just amplification. If you see someone with something behind their ear and there's something going into their ear, that's probably a hearing aid. A cochlear implant works a bit different because if you become too deaf, then actually you don't get any sound through at all anymore. So amplification doesn't work. And in that case, we're going to try to directly stimulate these nerves instead of having the hair cells move in this fluid because the hair cells don't work anymore. We're just directly going to stimulate the nerve with electrical stimulation. And then you can see here that the cochlear implant actually consists of two parts. There's the actual implant that is with a little spiral at the end implanted within the cochlea. And there's all kinds of electrodes in there that can make electrical signals to make the nerves respond to that. And there's also an external part that you wear behind the ear, but you can see now, of course, there's not going anything into the ear because the sound there doesn't get amplified anymore. The connection is actually wireless going through the skin, and it's with a magnet that is held in place, and it's a wireless communication that goes through the implant. Now, I have a small demonstration of how a cochlear implant works to maybe have a nice, more interactive demonstration about this. So I will quickly open my demonstration, and if it should be right. Now my microphone input is being directly streamed into this program. So what you see here is basically the instantaneous loudness of me talking. This is the top line. Here at the bottom, you can see the frequency analysis of my speech at the moment. On the left, you have lower tones. On the right, you have higher tones. And what a cochlear implant does is it makes use of this frequency selective sensitivity of the hair cells or the nerve cells in the cochlea to map, for example, the lowest frequencies when I'm talking to the end of the cochlea, so to these electrodes that are here. And the high frequency content is actually being stimulated with electrical pulses at the base or the beginning of the cochlea. So basically, I can now make a high tone, and then you will see an S, for example. You see that's mostly high frequencies. And when I do that, you will see here in the beginning more electrical pulses being activated to make this person hear again. So now we can also think about what does it sound like to hear with a cochlear implant. And actually, it is not very well, for us normal hearing people, or maybe there's some people with a cochlear implant in the audience, but it's very difficult to imagine what it sounds like because, of course, the brain of someone who learned to hear with a cochlear implant works very differently. But we can kind of simulate this by doing the same frequency analysis on a speech signal, and then just trying to reduce the frequency content and map this to a few electrodes, and then instead of making it electrical pulses, just play it as sounds again. And you will see I have a few songs here, and I will play a few of them, and I will increase the frequency content gradually, and let's see if you can understand what the sound is. So this sounds very blurry, but you can very clearly hear the beat, and the beat is something that cochlear implants are very good at transmitting. So here there's a bit more frequency content. So I don't know if you recognize this, but this is the original song. You can clearly notice that there's a very big decline in the niceness of the signal, like the frequency content. It's a lot degraded. If you have a song that, for example, starts with a guitar, this tonal content is very difficult to transmit. So for example, this is a guitar that starts. And this was the original. So as you notice, the tonal content is very bad. It's difficult to transmit. It's not that it's bad, but it's just something that people with a cochlear implant have to get used to. It's also very difficult to hear if someone that's speaking is talking with a male or a female voice, because this is a frequency selective information that is being transmitted.
Hij werkt al meer dan 10 jaar.
So yeah, so that was a Dutch sentence, but this gives a bit of an idea of how it would be to hear, or like the kind of information that you can transmit through a cochlear implant. But I could play with this demonstration all day, so now I'll go back to the presentation. I hope this was kind of clear how a cochlear implant maps, let's see, the frequency content to different parts of the cochlea, and that's how people with a cochlear implant can hear again. Well, cochlear implants actually work quite well. It's one of the most successful medical prostheses, but it's also, there are some issues with it. And one of the biggest issues is something that we call as engineers, we think about sometimes about processes and loops. And cochlear implants are basically an open loop. That means that there is no feedback mechanism. If you hear a sound and the cochlear implant processes it and stimulates the brain, there is no feedback mechanism. You cannot say like, oh, this is now good or bad, and that the implant adapts to that. This also cannot take into account, for example, when there is, if your hearing loss starts to get worse over time, your implant keeps the same settings all the time. So that's actually not very good. But to remedy that, people with a cochlear implant can regularly go to the clinic or to an audiologist, and there they can have some way of temporarily closing the loop by performing an audiological test. So they have to listen to some sentences and say how well it sounds. And they have a subjective response that they then give to the audiologist. And then the audiologist can play a bit like a DJ and adapt all the buttons in the implant and then try to make the sound better. But this is only during fitting in the clinic. In everyday life, when they go back home, you have to hope that your settings are good. Because yeah, it will be until the next clinical visit that you will have to have those settings. Another thing that might be disadvantageous about this is that we're making use of a subjective response. So the person have to indicate, oh, it sounds good or it sounds bad. This can be very difficult, for example, for deaf children with a cochlear implant, because they cannot communicate very well about how they hear. So how are we going to remedy some of these problems? Now here they are, the auditory brainwaves. And this is based on the idea that if you have a brain, like here on this slide, and you're presenting some sound to it, it will also present some kind of a response going up and down. This is some electrical activity of the brain. These are neurons firing in the brain. And the nice thing about this is that, for example, if the sound is lower or if the sound is suddenly absent, you can see this reflected in the brainwaves. So actually, this is an objective way, by just looking at the brainwaves, not asking the person how loud it is, to see how loud is a sound, or are you hearing sounds? Now, the previous diagram was a bit simplistic, but actually real brainwaves, auditory brainwaves, they're quite complicated, and there's a lot of peaks, and there has been a lot of research going into this. And there are so many peaks because actually, when I talked about a bit earlier, the cochlea transmits the sound to the brain, and there the brain processes it. There's a lot of stages in the brain processing of auditory signals that are ongoing. So you can see here some cross sections of the brain, and then all these pathways going through the brain, all the way from the cochlea to the brainstem, then going all the way up. There's also sound coming from both ears. At some point, it has to be integrated. So you can hear like where do sounds come from, like binaural hearing, and all the way at the auditory cortex. That's basically where the highest level auditory processing goes on. And all these peaks, you can see also on the horizontal axis, there is a time component. The further up these peaks appear, the longer the latency is. It takes a while for this wave to travel all the way through your brain. So it's quite complicated, but it can also reveal a lot of interesting information about how you hear, of course. Now, how do we measure these brainwaves? We have you have a lot of neuroimaging techniques to get a look at activity of the brain, but one of the most portable and easy and cheap ones is EEG, electroencephalography, where you basically put electrodes on someone's head, and you look at what kind of voltages come out of it, like electrical activity. So every electrode that you put on someone's head can give a certain signal, and that is then an EEG signal. And you can have up to hundreds of EEG channels at the same time. You can only use one. It's up to you, depending on what you want to investigate. So now that we can measure these brainwaves, let me see if I can go to the next slide. Yeah, which brainwaves are we interested in our research? Well, if we want to, the main parameter that we want to optimize with people that have a hearing loss or deafness is not just hearing sounds, but understanding speech. That is the main parameter that we want to improve, because that's also the most important for most people, just being able to understand conversations and listen to the news and understand stuff. There is a certain type of brainwaves that are speech tracking brainwaves. And that means that if we have a speech signal here, you have also speech envelope, like the outline in red, this instantaneous loudness kind of. This is being encoded in the brain or being tracked by the brain when you're listening to something. You're listening to me now, so somewhere my voice is being represented in your brain. And what we're going to try to do is look at brain recordings and try to reconstruct or decode the speech that you're listening to from your brain recordings. And we're going to do this using some advanced machine learning techniques. These are also techniques that are very recent now in research and have been developed only in the last 10 or 15 years, thanks to increasing computing power and machine learning and AI and all those kind of buzzwords. So the basic idea, to give you a bit of the concept for the people that are not familiar with machine learning, is basically that you always have two phases. You have a training and a testing phase. And in the training phase, you're just giving some examples of what you want your algorithm to learn. So basically, I'm training your machine learning algorithms now in your head with these data, and you have some numbers in the circles, and the output that corresponds to it is below it. And then I'm asking you, what is the pattern that you see here? What is the model? How do you decode this 2 from these numbers? And after a while, if you look at enough examples, you will realize, okay, it's just the mean or the average of these numbers. And now that you know this pattern, I'm going to give you a sample that you do not know the solution to. And then I'm going to ask you, now with what you learned, your machine learning algorithm has learned the model, what would be the answer here? And now you know, okay, it would be 5. And if your model predicts this correct, it knows it is 5, then you actually have successfully trained your model. This is exactly what we do with speech and EEG data. So we're splitting our data set in 2 parts, in a testing and a training set. And first, we're going to train the model on this training data. So we say, like, okay, machine, here is data for you to look at. There's an envelope, an EEG, and this envelope corresponds to this EEG. And now you're going to have to learn, look with your decoder at all this data and try to figure out a pattern. And once you looked at enough data, you can take this decoder and apply it to a part of data that you do not know the solution to. You do not know what is the envelope, and you're going to use your model that you learned to predict the envelope. And then we ask the question, okay, we predicted or we decoded this envelope from brain recordings. How good is this answer? And the better this answer is, the better our model can decode this envelope or this speech signal from our brain. The better, actually, this has been shown in research, the better the speech has been understood. So it was better encoded in the brain. It was easier to decode. So does this actually work? Well, here you can see some values of what we measured in people with a cochlear implant. And you can see the further you go to the right, the easier it was to understand the speech for these patients that we tested. And you can see all of these lines going upward in an upward movement. So that means that our speech tracking values that we get, they correlate with how well they understood it. It is higher if they understood it better. And this is nice because now we have an objective measure of how well someone with a cochlear implant understands speech. And we didn't have to ask them anything. We can just look at their brain signals when they're listening to something. Your outcome value, so this neural envelope tracking as we call it, is this high. So you understood speech this well. And this is very nice because it's an objective measure. So that's nice, objective test with brainwaves. That's, as I said before, for example, if you can apply this to children, you don't need to ask them how well do you understand it because they cannot answer the question anyway. Very nice. But if you look at the grand scheme of things, in the beginning I said, yeah, does this really now save or solve this problem of this open loop that you have in your everyday life? Because what you did now is you replaced an audiologist asking questions to someone being tested with, come to the clinic and we put an EEG cap on your head. And from that, we will derive your hearing and you don't have to participate in the test. But still, when you go home, it's still an open loop system and it will not adapt itself. We're still kind of stuck in this scheme, like where there is only an infrequent adaptation of the settings of the implant. And now there's a second part of our research that comes into play here. And that is by basically realizing that, well, a cochlear implant has a lot of electrodes in it. Basically, I didn't tell this before, there are electrodes in the cochlea, but there's also some extra reference electrodes. And you can stimulate between 2 electrodes here. But there's a lot of other electrodes that at that moment are not being used. And EEG is basically looking at the voltage difference between two electrodes. So why don't we just take two other electrodes that are not being used and look at the voltage between that? And there we can have our EEG measurement. And you can do that in a lot of different configurations. You can also stimulate between two intracochlear electrodes and then record EEG in another configuration of electrodes. Seems to work very nice. It's a very elegant solution because then you can just measure EEG at people's home if they have a cochlear implant. The problem is, why is this not being done yet, is that this is a wireless system. So you actually need to get the EEG recordings out of the implant again. So now the implant is very optimized. It doesn't consume a lot of energy. There's not a lot of dedicated recording hardware and software in there to look at these EEG responses. So yeah, this is actually a hardware constraint problem. We cannot use current commercial implants to make long speech tracking recordings of a brain. So what did we do? We actually cooperated with a manufacturer of cochlear implants who have a special experimental implant that is actually not wireless, but there's actually a plug in the side of the head. And with this implant, we can actually measure directly from the electrodes. We can, on this plug, we can on this plug here, we can attach our own measurement devices and then try to record directly from the implanted electrodes. And that is actually what we did. I will not be too long on this slide, but these are basically some plots of the first ever continuous EEG recordings that we managed to record using an experimental implant. So these are EEG recordings coming directly from the implants itself. And then you can see, for example, the top line, you can notice these positive peaks that we then label, and then we can see, oh, this is at that place in the auditory cortex or wherever in the brain, and this gives us diagnostic information. If we put these puzzle pieces together, we can actually think now about smarter hearing devices, because we can now imagine that instead of having this open loop signal, we can just have an implant that can directly record signals from the brain and adapts its own settings based on the EEG that is being measured. And you're not relying anymore on an audiologist that has to ask you questions or look at your behavior to see how well your implant is stimulating or how well you're hearing with your implant. So this is now actually a closed loop cochlear implant. And this is what we call smarter, because these devices, they also need to have some decision capability to see like, oh, the EEG signals are going quite bad. How am I gonna change my stimulation settings? And then, indeed, in the future, this will be a very nice application where we have also hearing aids that might have an electrode and also cochlear implants that are smart and are self-adapting, a bit like a self-driving car, but then a self-steering implant that can always provide the best hearing quality to the user and can also very quickly adapt to new circumstances, like you're sitting in front of the TV and then you're going outside to talk with someone. Your settings can change based on the EEG. So it's very adaptive. This is the talk about the things that I talked about just up to now were things that I researched during my PhD, but now we also started thinking about who else might benefit from this objective test, maybe not only people with a cochlear implant, but just very young children that you're trying to assess how well they understand speech, for example. It's at the moment very difficult because an audiologist, they really have to make a game and put a lot of time into playing with children to see how well they understand speech. For example, you can see a child that has to point at certain pictures, like, is it a bear or a pear, or what sounds did you hear? And this is a very time-consuming and also not always a super accurate test. Furthermore, you have young children with cochlear implants that might need some diagnostics of their hearing and that cannot really respond. You have people that are in cognitive decline, or you have dementia, and of course they are not super clear anymore, so they cannot really indicate how well they want to hear. People in a coma, you can always wonder, do they understand us or not? If you can look at their brain, you don't have to ask them. You can just see, are they tracking my speech? Are they responding to it in their brain? So these are a lot of clinical populations that we recently started applying these techniques to, and that we want to actually bring to the clinical practice, because there's a clear need for this kind of objective tests. So what we are currently working on in our research group, me and some colleagues, is estimating hearing with objective tests like EEG in young children. And you can see that instead of having to play and answer questions from the audiologist, they can just sit in the chair and watch their favorites. In this case, there's a lot of bears on the screen. And then we can just analyze their EEG and see how well they are tracking the speech and get some diagnostics from that. And indeed, this works. This is similar. You can see that the envelope tracking increases up to a certain point. And then, yeah, it becomes too easy. They understand everything. So then the line becomes flat. But you can kind of find for children the point at which they do not understand speech well anymore. And we're not just doing this for young children, but we can also do this, for example, with, yeah, this is a young child, but then with a hearing aid. So we can see, is there a benefit from wearing the hearing aid or not? And we can even go to very young children that are only a few months old. And as you can see, he doesn't really mind the EEG cap on his head too much. And here we were investigating how the speech is being tracked when his mother is talking to him. And then we can see, of course, he's not understanding the speech, but we can evaluate the peaks in these brain responses. So the future vision we have for this objective testing in audiology using brainwaves is a system that a child can use. It's watching a video or whatever. EEG is being measured. This is being processed in real time in a cloud. It gives some diagnostic, and then an audiologist can give the proper treatment to this child. And these are things that don't exist yet, but we're really convinced that yeah, this is one of the possible future paths for audiology that could really benefit better hearing rehabilitation for a lot of people. So I went a bit over time, so I'm sorry for that, but let me conclude with my take-home message, which is that brainwaves reveal very interesting information about how well we can hear sounds, and there's a lot of complex things going on in the brain, and we're still trying to unravel all of this. These brain-based tests, they are objective, so they have many promising applications for hearing rehabilitation, also for patients that cannot communicate well, such as people that are in a coma or very young, have dementia. And we're still doing a lot of research into unraveling how all of this works, but the first real applications are on their way. Also thanks to efforts of my colleagues in our lab here in KU Leuven. I would like to thank you for your attention. I hope you found it interesting. You can always connect to me or send me an email if you have any further questions or want to take contact about something. And also, yeah, this is not a one-man project. We have a very nice research group, ExpoL, which, there's a lot of happy people there that are very talented and smart and working on the interdisciplinary field of neuroscience and technology. So couldn't have done this without all of them and their support. So thank you very much for your attention. And now we can have a little discussion about if there's any questions or if you still have things you want to raise. Thank you very much.
Well, Ben, wow, great talk and lots of information. I'm sure there are a lot of burning questions. So, Vrone, how about you will fire the first one?
Yeah, I certainly do have questions. It was super interesting, Ben. Thank you. I was wondering if a cochlear implant, is it something that's also used for elderly people who just have hearing loss due to their age, or is it just the amplifier that they get? Like, who is really the target group for this cochlear implant?
Yeah, so for a cochlear implant, we don't really look at are you that old or what population do you have? There's just some criteria about how bad your hearing loss is. So you can go up to a certain level of hearing loss, and then you are still helped with a hearing aid, and then it becomes too bad for a hearing aid, and then you can be implanted. And this can be children that are born deaf or people that are 90 and still, suddenly due to age have too worse bad hearing.
Yeah, but like up until today, this hearing loss with the amplifier or the hearing aid with the amplifier is a bit better for hearing quality right now.
If you have a hearing aid, you still have a lot more residual hearing. So that means that your hearing quality, you still have some frequencies and it's not so bad. So generally they still have better hearing. Electrical hearing with a cochlear implant is just very different. You could also hear it in the simulation. It takes a long time to get used to, and some people, unfortunately, they don't really get used to it or don't get a good hearing quality from that.
Yeah.
So maybe a follow-up question or related question to it. So then is do people who are naturally deaf, so they are born deaf, are more sensitive to this implant compared to people who, for instance, they have a car crash and then all of a sudden they lose their hearing? Are there different responses, and do you also see different responses in the brain as well?
Yeah, so different responses. I don't really know about that, but there is something called cortical plasticity, or like the brain relearning and adapting to new inputs. And you notice very clearly that with children that are born deaf and they never learned language or learned to hear in a normal way, they grow up with it and they see it as the norm from when they are young. So usually they perform a lot better compared to someone who is 40, has a car accident, and then has to relearn the way they heard all their life already. So this is just about how adaptable is your brain to dealing with these new stimuli. So yeah, there is some variation in whether you are postlingual or prelingually deafened, but yeah, these responses, you generally find them in all kinds of populations, as long as they can hear. Yeah.
Yeah, and maybe actually related to these, Sha also had a question on the chat. So does the EG machine learning process also take into account children's language and brain development?
Yeah. So sorry.
No. It's
yeah. So the EG machine learning process. Yeah. Oh, yeah. So it depends a bit on what you are trying to look for in the EG signal. So at the moment, I talked in this presentation about these speech tracking responses, and they're basically responding to very acoustic features of speech. So like how loud is it at the moment, and this speech envelope is being tracked. And you can also include other types of features, like for example, or information about the speech that you're trying to decode. For example, like the language knowledge, or more like understanding features, like if they know what the words mean. And then you can have different machine learning algorithms trained on that kind of speech. So you can adapt your machine learning to different kinds of language knowledge or different brain development of children.
Yeah. And yeah, maybe Sha, related to this, that there was some small mishap. So the closed loop, is it limited also to language, and how well is it adapted to multilingual environments? So people who speak more than one language.
That's a good question. So there are some studies, but the results are sometimes a bit controversial. But usually when you are listening to something in your native language or your mother tongue, then the responses are best. And it is, of course, higher response if you understand the language that you're listening to. So imagine that you would wear this closed loop device and you come outside and someone starts talking to you in a language you don't know. Yeah, probably the results will not be that good, but you also wouldn't really understand the language. But this influence of different languages is still a topic of research. So yeah, it's not entirely known yet, like how different languages are represented in your brain.
Yeah. Someone also had a question in the comments. So he says it's very interesting, your demo that you did. And he also says like that he assumes you know the recent movie Sound of Metal. I personally don't know it. Where the main character, I think, then gets cochlear implants. How close to reality is what we see in a movie? So if you know this movie, can you give us a bit of background?
Yeah. I have to admit, I didn't see it, but I heard of it, and I was recommended it, that it's very good. It's actually about a drummer that's, I think, or a musician, I think a drummer that becomes deaf and has to learn to hear again with a cochlear implant. I can't really comment on the content of the movie, but I can refer back to what I said earlier, that a drum is a very rhythmic instrument. So it's actually quite possible that someone with a cochlear implant is very good at playing drums, because it's this rhythmic information that you can still hear very well and then play. But musicians that play a tonal instrument like a guitar or piano, they usually cannot enjoy their instrument that much anymore, or cannot listen to the tones that well anymore, because of a cochlear implant degrading the frequency resolution of what they are hearing. So
yeah, and also commenting on let's say musicians, because a lot of times you hear that they have some kind of not only hearing loss but also tinnitus when they have these sounds, this high beep in their ears. So could you, or do they use cochlear implants for or possibly curing tinnitus? Because if I'm correct, like tinnitus is a sound that's created by the nerves itself to descend to the brain, and this is not really a real sound that you're hearing, but it's made up by the brain. So if the cochlear implant is also transmitting some electrical signals, could you maybe correct for this with the cochlear implants? Or is this a stupid question?
Yeah, no. I'm not an expert on tinnitus, but it's indeed some kind of background brain activity or nerve activity or the brain interpreting that there is sound that there's actually not. I know that some people wear a hearing aid or maybe even a cochlear implant with a little bit of electrical stimulation to have a bit of a background hum or a background noise at all the moments, just to suppress this annoying beep that I hear all the time. And that way they cannot focus on it, and actually they don't cure their tinnitus, but they don't focus on it that much anymore. But there's not really a cure yet for tinnitus, and usually it's restricted to these kind of solutions where you use a noise machine or a hearing aid with a certain tinnitus program or something like that.
Yeah.
So yeah, and now going back a bit to this sound as well, because you showed that, for instance, a person with a cochlear implant would not distinguish whether it's a female or a male voice. But so I think that pitch somehow is hearing both, and I thought pitch had to do with frequency. So how does it work? Why is not really able to distinguish this thing?
So it's men generally have a lower voice than women, and this is indeed the pitch or like the ground frequency of your voice. And you have to imagine in your cochlea you have thousands of hair cells, and they're all very sensitive to a specific frequency. And with a cochlear implant, you're replacing it by maybe 20 electrodes. So the resolution of frequencies that you can hear is very much distorted. And this is also why the ground frequency of someone's voice is not represented so accurately anymore. And you can confuse male voices for female voices. But that doesn't mean that people with a cochlear implant don't know if a female or a male is speaking to them. They learn to recognize voices in their own way. It just sounds different to them, and they have to adapt to this new way of hearing.
Is it then an option to include more electrodes in there so that that it will be better for them to hear better sounds or distinguish between sounds?
Yeah, so interestingly, it is actually not better to include more electrodes. It is technically possible, and research has been done to this, but the problem that you're facing then is basically called spread of excitation, which means that if you're having this excitation, so the electrical stimulation targeting these nerve cells, you cannot never make it as accurate as one hair cell triggering one nerve cell. This electrical current is running through a lot of nerves at the same time. And yeah, it's all overlapping, and you cannot really get a good resolution. Even if you use more electrodes, they all have overlapping stimulation patterns. So that's basically the challenge that is also being faced in research for how to increase this frequency resolution. Yeah.
But then this EEG measurement could help with that better, right?
So EEG is more about looking at how is the brain responding to sounds. It couldn't really help, I think, with how to increase the resolution of the stimulation. That's purely a technological challenge for designing these electrode arrays and trying to make them more precise.
Yeah.
And then in another topic, so Wolfix Peace asks, actually, are you working with researchers working on brainwaves but for other sensory signals? So I assume maybe sight or taste? So
in our research group, we're specialized in hearing research. So the answer to this question is no, I'm personally not, but there's a lot of parallels, of course, with visual responses. You can also have visual stimulation and then look at how the brain is processing this. And yeah, there's also, it's not as successful or as clinical yet, but for example, for blind people, you can also have like a retinal implant that is stimulating the optic nerve in a similar way that a cochlear implant stimulates the hearing nerve. And in that way, blind people can already see again like light and dark and vague patterns, but it's a bit more of a complicated problem because if you restore sight, it's like a two-dimensional image, whereas sound is like a waveform or only the temporal structure that you have to get right. So that technology is not as advanced yet, but there's similar patterns about using brainwaves to improve those kinds of technologies. Yeah, but I'm not an expert in that.
But if you're measuring now the EEG, I mean, together with with your hearing the cochlear implants, does it? Maybe this is a stupid question. Does it have, or does it need a battery for this that you need to charge, or like how does that work? That the EEG is measured, like where does the energy for this come from?
You mean measuring the EEG with the implant itself, or?
Yeah, or yeah.
Yeah. So actually, a cochlear implant. Yeah, I know. For example, pacemakers or brain stimulators, they sometimes have to have their battery replaced in a surgery. The nice thing about a cochlear implant is actually that it is inductively charged from outside. So you never need to replace the battery. So when you see someone with a cochlear implant and they have this magnetic link on their head, it's actually also transmitting power from the outside device to the inside. And this is powering the stimulations parts on the inside. And if we want to record EEG from the implant itself, of course, that will also cost some energy to do that. And then the challenge will be to indeed make energy efficient electronics for the implant, or have bigger batteries that are worn behind the ear and then transmit the power like that inside. So that's an engineering challenge to consider for these closed loop implants.
Oh, super interesting. But then if it has this magnetic thing, then probably like can you take it off at least? Like if you have to do an MRI, which is a magnetic resonance imaging, like can you take it off to do this, or you just avoid doing an MRI altogether? Then
if I'm not mistaken, I think there's MRI compatible implants, but yeah, I'm not sure. I think generally they try to avoid it because sometimes when the magnet moves, of course, then you need a surgery because your implant doesn't work anymore.
Yeah. Okay. Super interesting.
Indeed, and maybe we can close with the last burning question of Sha. So, do they need to shave the head in order to have the electric transmission on the skin?
I'm not sure what you exactly mean with the electric transmission. Do you need to shave your head to get a successful EEG recording from you, or yeah?
I would expect her from the cochlear implant.
Yeah. So the implant itself, it's just like in your head, so it doesn't have anything to do with the. I mean, it's a wireless link. So if you have an implant, it just sends the energy and the information wirelessly inside, even through your hair. And also, hair is not really a big problem for EEG measurements. You just need to, usually when we do these experiments, we never shave our participants. We just try to stick them a bit so they make contact with the skin between the hair, or we use this kind of conductive gel to make the conduction better. But I've never had to shave heads of someone to perform an experiment on them with EEG. So luckily. Yeah.
Wow. So, well, Ben, thank you. It's been amazing. I think that we've all learned a lot, a bit, or definitely a lot. I've learned a lot. Maybe other people knew a bit about it, about the cochlear implants and the new coming ways of hearing. So, thank you very, very much.
Yes, thank you. It was super interesting.
Thank you very much for giving me the opportunity to talk.
And now with this, to all our very listeners and watchers, we are closing now Pint of Science Belgium 2021. We hope you really enjoyed this nice event as much as we did. We would also like to thank all the organizers. So we are just the pretty, or in my case, not that pretty faces that have been with you during the festival, but there has been a lot of amazing people also working in the background, and without them, this wouldn't have been possible. So did you miss any of the other events? Here they are all in the YouTube channel, so please be our guest and enjoy again all these events. And we are very happy to tell you already that Pint of Science 2022 has the official dates released. So it will be, if I'm not mistaken, on the 9th, 10th, and 11th of May 2022, hopefully live again, sharing beers in the bar. And with this, we close up this amazing event. We thank you for your attention, and we look forward to meet you in a bar in Pint of Science 2022. Bye-bye.